Cool, so this is the second half of lecture 5.4. You should have just heard 15 minutes worth of me talking about the fundamental theorem of calculus, and we're just going to do these last few examples in this video. It's pretty short, but make sure you watch the other one first. So take a look at the problems on screen. Just like before, we've got 4 functions, and each of these functions has an output that's defined using an integral. And you, at this point, should be pretty comfortable recognizing that x is the input, and each of these different y values represent a different area under a different curve. But there's something different about these examples that we didn't see in the last one. What's different? Exactly. These have terms of integration that involve expressions with x, not just a single x. And as you may have guessed, the fundamental theorem of calculus only applies when you have a singular x on the top limit of integration. So what can we do? Well, let's look at the first one together. We want to find the derivative of this function. This is a function. We want to find its derivative. So we would set it up like this. But then we hit a wall, because if I'm not allowed to use the fundamental theorem of calculus to take this derivative, and I'm not, because this doesn't have a singular x on top, then I really don't know how to take the derivative of this function. I know that I have to be able to. The fundamental theorem of calculus gives me that much. This has to be a differentiable function. But how do I actually take the derivative? Not really sure. So anytime we're not really sure in this class, I've always encouraged you to try something that you do know how to do. So looking just at this integral and forgetting about the derivative for a minute, normally, at least before this video, when we took integrals, definite integrals involved finding an antiderivative and evaluating the antiderivative at these two numbers. Well, now we have a variable instead of a number, but we should be pretty comfortable plugging in variables. They can act basically like numbers. So since I don't know how to take the derivative of this expression, let's try that. And I'll go ahead and hint to you that the work we're going to do right now is actually a long version of ultimately how you'll evaluate this, but it's important to have this idea in mind, otherwise you're going to forget why we do what we do later. So go ahead and follow this one with me. As we just said, our idea was, let's try evaluating this integral. And evaluating this integral means we would want to take an antiderivative. The antiderivative of cosine is sine of t. And then I'm going to go ahead and evaluate sine, and this line says evaluate, at 1 and at x squared, and then I'm going to subtract the 2. So this integral all on the inside is going to equal sine of x squared minus sine of 1. And that's evaluating the integral the way that we were doing before using the antiderivative. Now, of course, that's just the value of the integral. So next, if we really want to take the derivative of this expression, we would take the derivative of our result. And when we take the derivative of sine of 1, that's just a decimal number, so that's going to go away. And the derivative of sine of x squared is going to be a chain rule. The derivative of sine, of course, is cosine, and we keep the inside function x squared, and then we multiply times 2x. Okay, so this is actually the answer to this derivative, but you should notice something about the answer. First of all, cosine is the same as the function inside of the integral. That's kind of sounding a lot like the fundamental theorem of calculus, where we just took the inside function and had it equal the derivative. In fact, this is exactly the same principle. We're kind of undoing the derivative and then redoing the derivative. It shouldn't be surprising that we end up with the same function coming out at the end. But then there's something tacked on at the end, and this tacked on piece is the derivative of the x squared. So indeed, we can use the fundamental theorem of calculus if we think about it using a chain rule. So in the future, when you take derivatives of functions that are defined by integrals, where one of the terms itself is an expression, not just a single x, you can go ahead and use fundamental theorem of calculus and say the derivative of this expression is cosine of x squared. And you just need to remember to multiply times the derivative of that expression, in this case, 2x. Better way to write that would be 2x times cosine of x squared, but ultimately, that's it. Again, when you do your examples, if you understand where this 2x came from, you're welcome to just directly use fundamental theorem of calculus with the chain rule. If you do not understand where the 2x is, rewind to understand this work, and then ultimately your goal is just to go straight to the answer. Go ahead and try number 4. See if you can do it the same way that I did this one. Nice, so number 4 hopefully was fairly easy. In this case, the chain rule was used because of the x cubed, and the derivative of x cubed is 2x squared. Make sure that you remember to multiply the entire expression, and oh my goodness, this is a huge typo right here. This ln, I totally missed that there was an ln here, so this should just be ln of 3x plus 1, and in that case, since it's ln, you can't actually multiply these. Ignore that, so sorry. That's number 4. Okay, number 5 has something else different, so I'm going to do number 5 with you. What's different about this one? Right, so this time we have 2 different expressions as our terms of integration. And so, as you may expect, we definitely can't use fundamental theorem of calculus, and we can't even use it with 2 chain rules, because if you remember how we got that chain rule, it came from the fact that we were allowed to just eliminate the second expression, and the only chain we had was the first expression. If we had an x inside the sign here, because there was an x down here, this second term also would have a derivative, and that would mess up the entire pattern. So, what can we do? Well, the one thing we do know how to do is we know how to split up integrals. So, I want to take the derivative of this integral, but before I take the derivative, what if I reimagine this integral as 2 integrals, each starting at some common number? For example, 0. Using the same logic that we used back when we were doing definite integrals, the integral from 2x to x squared is the same thing as the integral from 0 to x squared minus the little bit from 0 to 2x. Imagine these like 3 numbers on a number line, 0 first, then 2x, then x squared. And in fact, this relationship is going to hold true even if x squared is smaller than 2x. So the relationship here allows us to rewrite a single integral with 2 different variable terms of integration as 2 integrals that have numbers on the bottom and variables on top. Now, each of these integrals are easy to find the derivative of, and luckily, when you take the derivative of a function, we have the difference rule, sum and difference rule, which says I'm allowed to just take the derivative of the front and subtract the derivative of the back. So now we have an easy way to find dy dx. We'll take the derivative of the first integral using the chain rule, and then we'll subtract the derivative of the second integral, and of course we can combine like terms. Try the same process with number 6. Model it after my work if you need to. And the answer looks like this. The last application of the fundamental theorem of calculus is a really simple one, and it's for creating functions. Suppose we want to find a function that has a derivative of tangent, and for which if you plug in 3, you get 5. Well, we really just want to write an equation here, and the beautiful thing about the fundamental theorem of calculus is you can guarantee a function's derivative if you just write the function as an integral. So if I have an integral and I need to pick something to go on the bottom here, but if I put x at the top and tangent of t dt inside, then when I take the derivative of it, it's going to have a derivative of tangent. So all I need to do now is actually just ensure that if I plug in 3, I get an answer of 5. And the sneaky way to do that is if you take that same x value 3 and you use it as your lower term of integration, and then you add 5 to this integral, look what happens if I were to plug in 3 to this function. Well, I plug in 3 for x right here, which makes this integral equal 0, because 3 to 3, same number, got to be 0. And then I add 5, boom, just like that, the answer is 5. This is your function. Try and do the same thing just for the last one down here. Find a function that has a derivative of 1 over ln of x, and for which f of 6 equals 1. and that would be this function right here. This concludes the fundamental theorem of calculus. You should understand the basic idea behind the fundamental theorem, both the first part, which was just a single piece of area relating to 2 points on a graph, and the second part, which said actually the whole function is related to each other in terms of their derivatives. And you should be able to find a function's derivative if the function's defined by an integral. That's it. I'll see you in class.